Okay, this is example number 1 of section 12.9. So here we have a cord at A that is being pulled at a velocity of 3 meters per second, and we want to know how these other cords, that all those cords pull out this weight D. So we know that since we are pulling that point A downwards, we will have D moving upwards. But we want to know how much is that weight moving upwards. So find the speed of the block D. And so we kind of, our common sense says that if we pull that here, that will go up. So as we see, there is only one string. So if we draw our string, so if we follow our string, we see that it's only one string all along right here, and that goes around here and end up right here. So it's only one length. So let's call that total length T. As soon as I pull here, everything will move because everything is connected. And to be able to calculate that, what I'm going to do is add all pieces of cords and say that all those pieces of cords are equal to L. So I'm going to have a reference that I will call datum, and I will name from here to here distance SD. So from here, from my datum to that distance is distance D. And then I'm going to name another distance from the same datum. I'm going to name that distance from my datum to A. I'm going to call it SA. So the solution will be that I add all the pieces of cord and then I make them the equals to LT. So I will say that I have one piece of cord, that is this one right here, that I name SA. And then this one that is here in the pulley is actually will be a constant. I can actually name that little cord, but tiny little piece of cord will never change. So if I ignore that little piece, you will see, because I am deriving after the expression that I'm going to write, and any constant, you know that the derivative of a constant is 0. So since this little piece of cords that are surrounding the pulley is always the same amount of cord, I will not write those pieces in my equation. I have this piece of A, then I have this piece that I call D, but that piece is D as well. It would be the same if that rope is attached to that or attached to the center. So actually I'm going to call this little piece SD as well, because it's actually exactly the same. So when you see that, if I want to have the whole cord, I could say that this is SA plus 3SD, and that's the total length that will be changing. Obviously, I could add, if you feel more comfortable, I could add these little pieces that will be constant. I just named it constant. So this is the expression that will describe my length of the total cord, and I will derive that expression. If I derive that expression over time, the whole equation is A plus 3SD, and I derive both sides of my equation. I see that the total length is, and that constant, which is the rope that is in the pulleys, is 0. So this is all 0. And that expression is A. Since this is a distance, the derivative of a distance with respect to time will give me the velocity and 3 velocity of D. And that is equals 0. So with that expression that relates the length of the cords, I can get a relation between my velocities. So this is the expression that I was actually looking for, because they want to find the speed of the block D respect to the speed of the block A. So I say that the speed of block D will be the speed of block A divided by 3. And it's very important not to forget this negative sign. Let me give me some space to make it clear. Why gave me the negative sign? Because that velocity was going downwards and that velocity is going upwards. And the velocity was 3 meters, so this is 3 over 3. And then I can say that the velocity of D is negative 1 meter over second. So they ask us to find the speed of the block D, and we get, if we pull the string with 3 meters over second, the block D comes to 1 meters over second. Why is that? Because the relation of all those chords. So we have 3 chords that will go up while we are just pulling one down.